Hi, Peter.
Hi there.
So this is Peter Kröner, and I'm going to ask you, Peter, to please talk a minute or two about who you are and what you do.
Yeah, I'm going to keep this real short because there's an introduction also in the recorded talk. So I'm just going to
Okay.
say, hi, I'm Peter. I usually do talks and workshops about web technologies. I don't do any real programming as a proper day job. Just talking about JavaScript is what I do. So I would say let's hand it off to my former self, my past self, and let him do the work, the talking. Hello and welcome to Scheduling and Interleaving with Generator Functions. This is a talk about a very specific problem that you probably shouldn't have in the first place. But if you do have this problem, then this talk is going to be very interesting, I hope. Hi, I'm Peter and I'm a trainer for front-end web technologies. I talk about JavaScript and HTML and CSS and TypeScript and so on. Not so much about frameworks, but more about the underlying web technologies. If this sounds interesting to you, send me an email and we can figure something out and maybe I can do a workshop for your company. Today we are going to talk about performance, and specifically front-end performance, and more specifically about the golden rule of JavaScript front-end performance, which is that every function must execute in 60 milliseconds or less. If your function takes longer than that, then the browser will start to drop frames and the user experience will degrade noticeably, simply because animations get choppy and everything just feels slow. Every JavaScript function must complete inside this time budget, or it must run in a web worker. But what if our function cannot fit in this budget? And what if the function can just be shoved into a web worker? Well, this is what this talk is all about. We are going to circle around this problem in 3 parts. First, we are going to take a look at how you would usually handle long-running functions and how you probably shouldn't do this the way that it's usually recommended. There's a very simple solution to long-running functions, but this simple solution results in unmaintainable code, and this is not something we are going to accept. Because we will end up with code that we don't want to accept, we need to explore this further. And the next step in this exploration is that we are going to take a look at the iterable protocol in ECMAScript, and from there on out, talk about the separation of concerns when it comes to handling long-running functions. This again will not lead to the most beautiful code that you can think of. So we need a third step, and this third step will involve generator functions, and they will basically make everything look and work just fine. The end result should be a pattern for dealing with long-running functions in JavaScript in general. Again, this is a problem that you probably shouldn't have in the first place, but if this is something that comes up, then this pattern will probably solve it once and for all. If you have any questions, ask me at the end. There should be more than enough time. Okay, let's start by talking about how you should not deal with long-running functions. And let's first explore the problem a little more in detail. Let's say we have a function and this function takes too long. It's a single long-running function somewhere in our front end and we cannot just get rid of it, it's just there. Now, this function by itself isn't the problem in our case. The problem is that this function takes too long. It contains a bunch of tasks, subtasks, and these are non-asynchronous tasks. They do something. Doesn't matter what exactly. It's just important that these tasks are not asynchronous and they are interdependent. Meaning that task B can only execute once task A has finished, because task B relies on the result of task A as input. The end result of this function is some sort of aggregate result. The tasks by themselves in this scenario are probably small enough that they can fit inside the frame budget, but the function as a whole cannot. To make things more complicated, we are going to assume that this function needs to execute in a performance critical environment, meaning the web front end, where we have to handle the frame budget and where we have to consider the frame rate. And to make matters even worse, for some reason, this function is not suitable for web workers. This might be because this function touches the DOM, which is not accessible in web workers, or because it relies on an API that's not available in web workers in some browsers that you need to support. So, this is the sort of problem that we are dealing with. And this sort of problem as a whole does not fit into our frame budget. What do we do? Well, the solution appears to be sort of obvious. The function consists of many subtasks, and we can then, of course, just implement interleaving. Meaning we do not simply execute the tasks one after another, but we add breaks. We split the function up and leave room for frames to render in between the subtasks. So we do a little work, render a frame, do a little more work, render the next frame, and so on. This is what I mean by scheduling. Interleaving is just the way that we schedule the function calls for the subtasks. The end result should be a nice smooth frame rate. So how do we actually implement this? Well, we could just use setTimeout and other timing functions, but there's a better way to do it. In this slide that you see right now, there's an animation when I move my mouse over the 3 boxes here. And you can see that they start to fill up with bars. And the rate which with the bars are drawn is dependent on how we schedule the drawing process. The lower 2 bars use timers. In one case, the function that draws the bars is simply throttled, and in the latter case, it's debounced. Debouncing meaning after new input has stopped arriving for some time, the next bar will be drawn. But the topmost box is the most important box, because there a bar gets drawn every other frame, meaning that this actually implements interleaving. We draw a bar, wait for the next frame to be rendered, draw the next bar. Let's try to implement this with our function that we've seen before. Let's take the function takes too long and make it, in a first step, an asynchronous function. We're not really dealing with promises at this point, we are just using callbacks to keep things relatively simple. But, of course, if we start to mess around with timers and callbacks, our main function takes too long also needs a callback, and this callback gets called at some point and takes the aggregate result of all our tasks. So that's the obvious part. Now comes the actual interleaving. For this, we rearrange the function to hoist the variable declarations to the top, and now we can simply take the entire task execution and wrap it in request animation frame. Request animation frame is a function that's available in every modern browser that takes a function and executes this function the next time the browser is about to render a new frame. If we take our code that computes A, B, and C and shove it inside request animation frame, we essentially implement a first step of interleaving, because we execute the function takes too long, and then only when the next frame is about to be rendered, we execute the rest. And if we repeat this process for each task, then we end up with something that sort of works like we intended. Because the function gets called when the next frame is about to be rendered, we call task A, then the next frame, task B, next frame, task C, and we are done. And this sort of works, it just doesn't look that nice. Now, if code doesn't look nice, it's not just a matter of aesthetics. It's usually something to do with the code having a more fundamental problem, and that's true here as well. What's the problem that is underlying this code? Well, it's that there's no separation of concerns. This function that used to do only one thing, compute our data, is now handling 2 different problems. It's concerned with scheduling, wrapping everything in request animation frame calls, and it's concerned with data generation. And this is just what makes this code so ugly. I mean, nesting callbacks doesn't help, but still, this is the underlying problem, mixing data generation and scheduling. And the result sort of works, it's just an unmaintainable mess. But, I mean, it's a first step. We have something that works, that actually performs the way we want it to perform. And we can build on top of this, I think. So let's recap real quick what we've learned so far. We wanted to keep long-running functions from interfering with the frame rate, and the way we wanted to do this is by implementing interleaving, in this case by just adding request animation frame everywhere. And this, well, did work in some way, but the code that resulted from this is just an unacceptable mess. But we've already identified the reason for the code being so messy. It's the missing separation of concerns, so let's talk about separation of concerns. The way we are going to do this is by first taking a look at something that appears to be not relevant to the problem, but it actually turns out to be relevant. And this thing that we are going to take a look at is the iterable protocol in ECMAScript. Let's start from the simple for-off loop. Do you know how this works? I mean, the for-off loop looks like magic. It can take any sort of list and then just iterate over every item in this list. The list could be an array, of course. In this case, an array of numbers, and this works. But we can swap out this array for basically every list-like object that you can think of in JavaScript. For example, we could use a set. Now, sets appear to be very similar to arrays in JavaScript, and semantically that's sort of true. I mean, both are lists of numbers in this case. But from an API perspective, the two objects are very different. Arrays, for example, have a length property that indicates the number of elements in the array. And sets have something similar, but it's called size and not length. And there's many more differences. But the for-off loop doesn't care about such differences. It just works no matter what type the object that we're operating on actually has. It can handle arrays, it can handle sets, it can even handle maps. Maps are also sort of list-like if you ask JavaScript. And more than that, it can also operate on strings. And this is very interesting indeed, because you might say that a string is just a list of characters, but characters are not really a thing in Unicode. Unicode only has code points, and the combination of code points that follow each other then result in characters on the screen. But stuff like the clown face emoji here are not really one code point, they consist of two code points. And the for-off loop somehow knows that in this case the number of items in the list in this case being a string, has to be treated differently for some special items like this Unicode emoji code point contraption. Now, how does this really work? The way this is implemented is that the for-off loop in fact doesn't know anything, but the objects themselves, the sets, the arrays, the strings, they know how they need to be iterated over. They all implement a protocol, the iterable protocol, and this essentially communicates to the for loop how a list-like object wants to be iterated over. And to illustrate how this works, we are just going to implement our own iterable object. To do this, we first need an object, and this object needs to have a method called symbol.iterator. Symbol.iterator is sort of a magic key, the magic key for the function that stuff like the for-off loop needs to call to get something that they can then iterate over. This method must return an object, and inside this method we can keep any state that we need for our iteration. In this case, we are going to iterate over a bunch of numbers, so let's keep numbers in the scope. Now comes the important bit. The object that we return from symbol.iterator implements a method called next, and next always returns objects. The objects returned by next always have two fields, value and done. Value, of course, has the value for the current iteration, and done is only true when we've exhausted the entire object, when we've iterated over the entirety of the array, for example. In this case, done is always false, meaning that we always get a new value, and this value is always the previous number plus 1. So this object implements an endless list of numbers, essentially. If we don't want our list to be endless, we can of course introduce a limit. We can simply wrap this in an if statement, and if x is 3 or larger, then we return something else. This something else is still an object with value and done, Only in this case, done is true and value is undefined, meaning that there's no new value because we are done. So this is essentially an object that we can stick in for off loops or any other number of JavaScript constructions, and this will then deliver 3 numbers when next is called. And there's many things in JavaScript that will call next. Iterable objects, like the one we just built, or like arrays and sets and so on, can be consumed in a number of different ways. For example, we can stick them into a for-off loop, of course. Or we can stick them into something like array.from, which will construct an array from iterating over the object, essentially calling next until the object is exhausted, and then taking all the return values and putting them into an array. Now, this is what we could do. This is what's boring. We can, of course, also call next manually. We can create our own little consumer. This can be very simple, in fact. We could just say, okay, let's have a value next, a value and the iterator. Get this from the iterable object by calling the method symbol.iterator, like we've seen when we implemented the object, and then essentially loop as long as done is not true, and just print the value to the console. Now, this is not the greatest code we've ever seen, of course, but this is just for demonstration purposes. We essentially call next until we are done. It's very simple. Now, this is the interesting bit. We can consume iterable objects at our own pace using our own logic. Let's concentrate on this for a minute. And let's ignore the for-off loop and everything else. This is obviously useful stuff. And useful stuff belongs into its own function. Don't you think? Now, when we've written our own function, we can rearrange this code some more, make it more readable, but the important bit is that we can now take this iterator object and consume it in a way that our function just defines by itself. Okay, let's make this a little nicer, let's have local variables and stuff, and now that we really have a proper function with a local scope, we don't really need the loop anymore, because we have a function and we are essentially doing the same thing over and over and over again until there's some condition that must be reached. This sounds like a job for recursion, don't you think? Okay, now this is the same as before, without a loop, with a recursive function. The interesting bit about recursive functions is that they can, of course, call themselves, or they can call functions that call themselves. We can recurse indirectly. For example, we could use something like request animation frame. Now look at this. We have the iterable object, which basically handles all the data, and we have consume, which handles all the scheduling. It triggers itself, scheduled by request animation frame. This sounds like a separation of concerns. We have done what we set out to do. Originally, we had all of our data in one huge function, and it was a giant mess, but now we can separate it into something that looks more reasonable. We have something that produces the data, and we have something that consumes the data. And the consumer implements essentially the scheduling, in this case via request animation frame, and the data producing process does not really need to know that it's being consumed in this way. It just handles the data. So, knowing that we have this consumes data function that uses request animation frame to trigger itself and to basically suck data out of produces data, we only need to rewrite produces data, or rather we need to rewrite our original function into something that can be consumed. And for this, we only need to implement the standard ECMAScript iteration protocol. How hard can it be? Let's take our original function, let's rename it to produces data, because this is more reasonable than takes too long, because by now the function doesn't take too long anymore, it just doesn't look very good. And let's turn it into something that works with the protocol. Okay, that's sort of easy. Let's first step back, remove all the request animation frame that we wrote into the function, because the whole point of this exercise is to get rid of request animation frame at this point. And then rewrite this function so that it is an object that produces an object that implements symbol.iterator and the next method. Okay, this looks different, but not exactly bad. This conforms to the protocol, but doesn't really conform to the spirit of the protocol. Because at this point, we are still calling task A and task B and task C in sequence in one go, and there's no interleaving possible. For this to actually work, we need to execute task A, return an intermediate result, and then only on the next call to next, actually execute task B. That's not that hard. Let's just add a variable to keep the state, to know at which step we are currently on. And then if the step is 0, if we are at the first step, let's call task A and then actually take a moment to not only, of course, implement the step value, but also to return an intermediate result. Now, this return statement is necessary for there to be a separation point where the consumer knows that now is time to call request animation frame and only then get the next value. But we can make this even more useful. At the moment, we return undefined from this first step and return an aggregate result in the last step. This is probably not necessary. I mean, nobody cares about the last step. The last step is only important to communicate that done is true. And returning undefined from an intermediate step is also not a good idea because we, at this point, have the result for A. So we can swap this around. Return nothing at the final step, using the final step only to communicate that the iteration is done. And we use our intermediate result to communicate the result of task A. And once that's done, we can also add steps for B and C. Okay, this again obviously works, and this implements the separation of concerns. Yeah, sure, but this still isn't the most beautiful, maintainable, understandable code. I mean, we've solved our initial problem. We've implemented separation of concerns, but I still have concerns about the concerns, if you get what I'm saying. Again, this is a partial result that we can build on top on. Let's recap real quick. What we wanted to do is to implement interleaving independent of data generation. We wanted to implement separation of concerns, and we did this by implementing the standard ECMAScript iterable interface for essentially our data generating logic. And this now works, and this now has scheduling independent of data generation, but the code is unacceptable. It's just unacceptable in a different way. But this is now unacceptable in a way that's way easier to handle than before. Before, the fundamental problem was that we had no separation of concerns. Now we have separation of concerns, and part of our original problem has been solved cleanly. We have our consumer function. We just need to have a better way to generate data, and well, speaking of generating data, generator functions are just what we need for this. So let's talk about generator functions. The easiest way to talk about generator functions is to simply show what they do. And to do this, we are going to start again at our original example for an iterable object that we implemented. Now, forget all the code that you see here and focus on the capabilities that the object here provides. What we get from this object is a way to call a function and then having an object that we can call next on. And we can call next on it and next on it until the list is exhausted. This is what this object actually implements. This is what we really need for compatibility with the iterable protocol. And this object that we built for this purpose is just one way to do it, but there's a simpler way. The simpler way is a generator function, and a generator function starts out as something that looks like a normal function. But then we add a star behind the function keyword, and this turns it from a regular or JavaScript function into something special. This is essentially a factory function for iterable objects in a more developer-friendly way. Inside generator functions, functions with a star behind the function keyword, we can use the yield keyword. And yield is something like a partial return, if you like. We can put, like in a return statement, any kind of JavaScript expression on the right-hand side of the yield keyword. And what's on the right-hand side there is what the returned object from the generator function is going to produce on a call to next. We can have as many yield statements as we like inside this function, and what this in its entirety now does is the same thing as our object did before. It's a sequence of 3 numbers. It's just way less code, and it looks a little strange. But again, remember that the thing we cared about was the interface that we can program this object with, and this is exactly the same as before. We call something, in this case it's the generator function itself, and we get back an object, a generator, that implements the exact same interface as we've seen before. We can call next, which will cause JavaScript to jump into the function, go to the first yield keyword, and produce whatever is on the right hand side of the yield keyword, put this into value, say that done is false because the function hasn't returned yet, and then pause execution. When we call next again, we continue from the point where we stopped before. So until we get to the next yield keyword, we get 1, we call next again, we get yield 2, and then, because this is a JavaScript function, there's an implied return undefined at the end. So for the final next, we get value undefined and done true because, again, an implied return undefined. This is what a generator function actually provides. It's a simpler way to implement this interface. This is all what they are. I mean, there's more to the yield keyword and generator functions that we could talk about, but today is not the day for that. For our purposes, it's best to know that they are just a developer-friendly way to achieve the goal that we've been chasing all along. And this goal, as you might remember, is to split up this function. This function takes too long. Let's try to do this with the generator functions. This is not going to be so hard. We add a star, we add a bunch of yield keywords, and we get rid of the return statement because we don't need it anymore. And that's it. That's the interface that we wanted to implement using this object construction from before, just in a very simple way that looks more like a function. I mean, technically speaking, this is no longer a function, but it reads like a function, it looks like a function, and you can mostly program it like a function. You can use if and else and loops and everything in this now generator function. And this is actually the real proper way, in my opinion, to add interleaving to long-running functions in JavaScript. You simply split up your long-running function into subtasks, task A, task B, task C, wrap the entire thing in a generator, yield intermediate results, and then write a consumer function like consume request animation frame, and then consume the data scheduled by a function that has nothing to do with the data, that doesn't even need to know anything about the data. Separation of concerns, baby. And you can also consume it all unscheduled. You can have different scheduler functions. You can take request animation frame to render a frame, get some data, render a frame, get some more data, or you can just use array from if you don't care about performance, if you just want to have all the data all at once. So this is how it works. First, turn the function that you want to have behave better, that you want to prevent from causing the browser to drop frames, turn it into a generator function. Then each bit of data gets released by the yield keyword once it's been generated, and then you combine this function with a consumer function that implements the required scheduled logic, and then you mix and match as required. And this is actually an important bit in my opinion. You can schedule depending on your circumstances. Maybe you have some bit of code that runs in the browser frontend where it's really important that the browser gets time to render frames in between tasks. Or maybe you don't care. Maybe you have a prototype where this sort of performance is not that important. If you are, I don't know, performing an experiment, or if you're writing unit tests. If there's unit tests, you only care about raw execution speed, and there's probably no frames to render, so why bother with request animation frame? Using this approach, you can simply generate data without thinking about scheduling, and you can schedule function calls without thinking about what you are actually scheduling. So, in the main frontend, you just use one consumer function for your task, and this must not block the main thread. This leaves time to render frames, and everything is hunky-dory. In your unit test, where you only want to have code as simple as possible and as fast as possible, and you don't care about dropped frames, well, you just use array from. You don't even need to write a consumer function. You can just use what JavaScript provides by itself. And this approach, for me, works really well. First of all, you can just write existing code and write more code and write code all day long until you notice that you've destroyed your frame budget and that you need to optimize for performance. In this case, it's really easy to apply to existing code. I mean, you add stars to functions and you sprinkle yield statements everywhere, and that's it. You have the advantage of interchangeable schedulers, as discussed. Your unit tests don't need to experience any drop in performance while you make the front end faster. You have a clear separation of concerns, and you don't need any third-party libraries at all. It's 100% vanilla JavaScript. I mean, you probably could use a scheduler function that someone else has written, but it's so easy that you probably don't need this. And the best thing is, it's also easy to compose, because there's not only the yield keyword, but there's also yield star. Let's say we have a really simple example, like before. We have task A, task B, task C, and our generator function takes too long that combines all the tasks and yields their results. Like we've seen before, just a little more simplified. But now imagine if you had something that's more complicated than that. What if task B by itself is also something that by itself takes too long and that has a bunch of subtasks, like this? Now task B also is a generator function, in this case with two yield statements inside, and this now does not deliver the results that we actually need. Consume request animation frame delivers first one from task A, and then the generator returned from task B, and then the result from task C. What we actually want from task B is what task B by itself generates, and not the generator that generates the data. But for functions that are actually generator functions that don't return data, but that return generators that generate the data that we care about, we can use yield star. Yield star, in this case, does not return the object that's right of yield star, but it actually switches to the generator that's produced by the expression on the right hand side. So in this case, takes too long yields the result from A, then switches to task B, gets 2 and 2.5 from task B, then switches back into itself and yields the result of task C, resulting in 1, 2, 2.5, and then 3. And this makes it not only easy to write, not only 100% vanilla JavaScript, but also very easy to build upon and to build very complicated applications, very complicated functions using this pattern. Now, there's of course also reasons to not use this pattern. And the most important reason against using this pattern is, again, and I have to stress this, you should not have this problem in the first place, probably. If you're just generating data, you should probably use a web worker. If you're only dealing with pure number crunching, that's totally possible. And generally in the front end, in the user's browser, you should probably not do any heavy lifting. I mean, theoretically, you could, I don't know, encode videos on the user's browser, but this might not be the best idea anyone's ever had. I'm just saying. But if you have this particular problem, and I just happen to have this problem 2 times in the past 2 years with 2 different projects, this might just be the solution you've been looking for. Another reason against using this pattern. Interleaving your function obviously slows it down, because you are not using all the runtime your function needs, but you're essentially adding pauses and breaks in between. This slows down the overall program, and this might be necessary. It's probably not something that you want, but maybe you want to make this trade-off. I don't know. And then there's also the fact that generators by themselves are not especially fast if you compare them to regular JavaScript functions. Generators and generator functions obviously are very complicated objects that keep a bunch of internal state. So yeah, they use a bunch of memory and they take a lot of time to create. So they also contribute to this slowdown. This is something you have to consider if you're trying or maybe thinking about implementing this pattern. But there's also reasons for using this pattern. And the most important reason here is that no matter the disadvantages, everything's better than blocking the main thread. If there's one thing you don't want to do in the front end is to drop frames. You want to keep every function call within your 16 milliseconds of budget. And if the only way to do this is to use a generator and take all of the disadvantages that we talked about and just deal with it, well, then you should probably deal with it. Another thing that's an interesting side effect of using this pattern is that you truly break up your entire function. Usually a JavaScript function runs to completion. It starts to get executed, and the next thing that happens in JavaScript only happens once your function has run to completion. That's not true with this generator function scheduling approach, because you add breaks in between. And this makes rendering progress bars very easy. You have actually frames where the progress bar can be rendered. You can actually see it fill up. And if you want to abort the execution, that's also very easy. You can simply stop calling next. If you have a procedure that you want to abort and still have a partial result, that's also very easy because you've been yielding partial results all the time. So this makes for a really good user experience. Someone starts a task, sees the progress bar fill up, the expected result appears on the screen, there's some more calculation that the user doesn't care about, they can just click cancel and have everything work like in a proper user interface. And of course, compared to everything else that you can use to implement something like this, this has zero dependencies and it's all standard ECMAScript, and standard ECMAScript that's ages old by this point. This works in every browser, and if you happen to support something, I don't know, from the Ice Age, you can still use Babel. Babel can still transpile everything to something that, I don't know, works in IE9 or what have you. I used this pattern for 2 use cases. I once was in the situation that I had to read styles from a browser extension. And by styles, I mean all the styles from all the elements. And in my current project, I'm generating animated GIFs on the client side. And this is also something that simply hogs the main thread and can be quite simply made user-friendly using this pattern. The first use case was a browser extension for a startup that's not active anymore, but our goal was to create a browser extension that basically compared your project web page to a style guide that you've created before. Essentially doing sort of DOM diffing on the CSS object model, if you like. For this, I of course had to read all the styles in the entire web page. And if your web page has a gigabyte, and if your web page has a megabyte and if your page has a megabyte of CSS and thousands of elements, this of course takes a bunch of time. And this time cannot be spent in a web worker because in this case I needed to access the DOM. Not even considering the fact that in a browser extension I don't have a web worker, so I couldn't have done this anyway. But with this pattern, we had a smooth user experience. The progress bar filled up, there was an abort button, and everything worked out just fine. It just was that no one cared for this particular feature for this project in general. And my other project concerns itself with generating animated GIFs. You've seen the code animated in this presentation. I'm working on something that can export this to video, of course, and to GIFs as well. And for the latter case, I'm just doing this on the client side because overall, this is simpler to build and faster for the end user to just generate this on the client side. But of course, this is a complicated animation. I need to compute a bunch of frames. I need to render this onto a canvas. And there is a canvas API for use in a web worker, but this API is not available in every browser. So I just do it on the main thread and render frames in between. Again, I get a nice little progress bar, I get an abort button, and everything works just fine. So if you are doing more than just churning out user interfaces with a front-end framework or something, if you're doing something special, there might actually be a use case for better handling long-running functions. So, to summarize, our original problem was that we had long-running JavaScript functions that caused frames to be dropped because they ran on the main thread and blocked the entire browser. The solution seemed to be quite obvious. We just add interleaving, add breaks for the browser to render frames, and split up the tasks. But the naive approach resulted in messy code, but by turning the data generating function into a generator function and writing a consumer function that has its own scheduling logic, we can make this work, make the code look nice without sacrificing too much in the way of overall performance or developer experience when it comes to writing unit tests and code readability and so on. At least I think this is a proper solution that works quite well for me. And if you have any questions, I'm happy to take them now. Thank you for your attention.
Hi again, Peter.
Hi.
So now it's time for questions and answers. And we already, I think, no, okay. So Klaus says it is fascinating every time during your lectures which size of JavaScripts one did not know yet, and your lectures always deepen the knowledge. Thanks a lot for the great lecture, Peter. Okay.
Thank you a lot for the kind words, but that's not a question technically.
That's not okay. People are uploading your presentation. Okay, so I will be the first one while we're waiting for other questions. So I had this thing in my head that generator functions are called functions, but they are not really functions, are they? Because they are because functions are stateless, as far as I know. But maybe I'm wrong on that too. And the generator functions are more like objects because they have states. Because otherwise, you couldn't yield. You couldn't use the result of the previous task. So for example, task B used the result of task A. And if you didn't have state, then you couldn't save that result, or it wouldn't make sense to use generator functions because you would need to complete task A again to get the result of task A, and then you're just back to where you started. You have a long-running task.
Well, I think the confusion comes from the fact that, well, first of all, functions can have state. When they return, they capture their scope, their enclosing scope, their closures, and they can still, well, they have, their state is actually the variables that they that were in the scope where the functions were created, and they still have access to them, so you can kind of think of them as being stateful. And they are not that different from generator functions in that regard, because the important bit is that a generator function is just a factory function for a generator object. So there's nothing special about the function apart from the fact that you can use yield and that there's an implicit return, sort of like a class. A class is also, you might say, a class has state, but the class itself doesn't really have state, but it is able to create objects that have state. So just in the way that a class is just a factory function for objects, a generator function is just a factory function for objects, but for a special sort of object.
I see. Okay. Makes sense. I also had another question about yield. So let's say that I want to simulate dice throwing, for example, and I want to throw dice until I throw sixes. I throw a 6. So can I do basically an almost or infinite loop with generator functions?
Yeah, sure. You can just do basically an infinite loop, like while true, and then have it yield the next number each time you call next. That's totally possible. I mean, it's kind of the kind of a canonical example for using generator functions, where you can represent stuff with generator functions or with generators in general that are not possible to represent in JavaScript otherwise. I mean, your dice rolling machine would in effect be an infinite list of numbers. But you cannot have an array that's an infinite list of numbers because, finite memory. But it's sometimes easier to represent stuff that's infinite and then just take as much from this infinite source as you need. And generator functions are just the tool for the job in this case.
Sounds great. So a very newbie question. So generator functions go until the result is undefined. Is that correct? Did I understand it correctly?
The generator function by itself doesn't do anything. You need to take data from it using next. By itself, it's just suspended. But it's able to generate data until the generator function has been terminated by using return. And you don't have to return undefined. It's just the canonical way of doing things. But a generator has actually three, let's say, types about it. There's the type that you return by using a yield. In your dice throwing machine example, that's a number. There's also something that you can return that's usually undefined, because if you have something like a for-off loop, you can't really access this last result, this value that you return alongside with done true. But you can, if you consume the generator manually, you can inspect this value. So it doesn't have to be undefined. The endpoint is actually when the object that you return has done set to true. And the value is something that you can choose by yourself. And there's also something that we didn't see in the talk, but that you can do. You can also pass input into the generator. You can pass an argument to next. And then if you have a yield expression in the generator function, you can actually write something on the left-hand side. So unlike return, where you just go return something, you can actually do, I don't know, let x equals yield something else. And then because your program in a syntax point of view is actually a tree, the right-hand side of this expression, something equals something else, has to be evaluated before you can assign a value to the left-hand side. So if you yield something, the program doesn't really, the generator doesn't really stop at this line, because lines are not really a thing in the terms of program execution, but it actually stops on evaluating the statement yield something. And then you can consume this something on the outside of the generator. And then when you call next again and pass a value, this value gets then substituted for the yield statement. And this is actually what ends up in the variable on the left-hand side of this whole equation.
You see, so you can yield undefined then.
You can yield undefined, sure.
All right. I had another question. So it's still a bit, so it was a bit confusing for me, maybe not for others, but for me, that yields go from top to bottom. What happens if I branch inside the generator function with ifs or?
Totally not a problem. The way to think about generator functions, if you're used to today's everyday JavaScript, then you're probably used to async await. And yield is sort of like await. It's just that in an async function that uses await, it's actually technically a generator function, just where the API contract states that await something takes something, wraps it into a promise if it isn't already a promise, and then yields this promise. And then there's a runtime function, a consumer for your async functions that's built into JavaScript. You don't notice that it's there. And this consumer takes the promise, attaches a callback, waits for a value, and then passes the value to the next call, so that it ends up on the right-hand side of your await statement. So it works literally the same way. The generator function is just the more generalized variant of async await. On the other hand, you can implement async await using just generators. You just need to write a function that expects the generator to yield promises, attaches it to callbacks, takes a value, passes the value to the next yield. So it's, if you know async await, you can use generators. You just have to incorporate the possibilities that generator functions afford to you into your mental model. You need to consider that there's stuff you can do with generator functions, like what we've seen in the talk, separating essentially your logic with regards to generating data from the timing. You just need to incorporate this into your worldview somehow, and you need to identify the problems that you can actually solve with this syntax. And this is something where most people struggle with generators. They can understand them just fine, they can read the syntax and everything, but what sort of problem can I solve with this? And this is usually something, in my opinion, that's related to time and callback, like async await or like interleaving, as we've seen in the talk.
So I think that this problem is somewhat related to how JavaScript is a single-threaded language and how it handles events. And this was a while ago. So some has multiple event queues. That's a complicated. I think that's, to me at least, a somewhat complicated thing to comprehend, how it handles the different tasks. Like has a different queue for more important and less important tasks, and tasks that need to be handled. But that's an entirely different topic. So sorry, I don't want to branch too far off into JavaScript land, because then we can go on and on for days. So you mentioned that this syntax is vanilla ECMAScript that's oldest time, and it's supported in every browser. I'm not. Is it supported in every browser?
Well, you of course think about, I don't know, Netscape or Internet Explorer or something from the past, but you can actually make it work in every browser, because if we again take generator functions and break them down even further, they are just, as you said, functions with state, sort of. And you can actually take a generator function and all its behavior and syntax and essentially translate it into even more basic JavaScript. This is what Babel does. So no matter how old your browser is, even if it's not supported by Babel, you can implement this behavior just fine using vanilla JavaScript, even if you have to support some, I don't know, really ancient system. It's not really that straightforward, but totally possible. You need sort of a jump table, a long switch statement, and a bit of looping, and it will look really strange, but it will work just like a generator function. It's really just that generator functions are essentially an abstraction on top of, or rather, a factory function for iterable objects, like we've seen. And the iterable objects, again, are just vanilla JavaScript, just really basic stuff. So it really works in every browser, because generator functions by themselves are really old, and if you have to support something really ancient, they probably won't work out of the box, but you can get the same behavior by putting in a moderate amount of work.
Okay, so that's how to work with something that's a bit more ancient, and how to work with something that's a bit more modern. How does generator functions work with TypeScript, for example?
Just fine. They work just fine.
I mean, is there a nicer way to define your generator functions? For example, would it look better in a type?
Can
you
they work with
an
TypeScript just
interface?
fine? I mean, the point is that what I've said before about the three types of generator functions, about the input type, the yield type, and the return type, this was actually my brain thinking in terms of TypeScript. Generator really is a built-in type in TypeScript, because it's a built-in type in JavaScript, and you can strictly define your generator to require a certain input type and to yield something specific and to return something specific. So it's a really nice match for TypeScript.
Okay, and unfortunately, it seems like I'm the only one who have questions. Yeah, you used request animation frame in the talk. Are there other ways we could do interleaving, other functions that we should consider if we encounter this specific problem?
Well, you can actually use anything you want, really. I mean, I just used request animation frame because the problem in my case was really related to keeping the animations nice and smooth. but you can actually use any scheduling mechanism that you want. I mean, you can have another function like you can have another function execute something, and only once this function has executed, then also take something from your generator. I mean, it's totally open to you. I mean, you could use something like set timeout that, or set interval or something. That would be sort of straightforward, but probably not quite as useful. I mean, again, what I said at the end was you probably shouldn't have the problem that this pattern solves in the first place. Because if you have something that's not related to anything in the DOM, you should just put your long-running code and shove it into a web worker. That's faster, easier, and you don't need to change anything. If you are in Node, you should just spawn another process, and that's the same thing. So you can use probably any function for as a timer for consuming stuff, but I struggle to imagine a scenario where you wouldn't use request animation frame.
Right. Okay. Makes sense. So that's also something that I wrote down here for me. I'm not really familiar with web workers. Can you say, since we don't have any questions from the audience, can you say a few words about web workers? Because I'm familiar with it. I'm mainly a Java developer. I confess.
Yeah, but if you're a Java developer, you know about threads.
Yes.
If you have something that's just a bunch of number crunching, you can offload it to somewhere else where it doesn't disturb, you clicking on buttons and stuff. And you cannot really do this in JavaScript with proper threads that work sort of seamlessly, because as you said, the whole browser environment is single-threaded. But web workers are sort of an exception if you have a bunch of code that really only does number crunching and nothing else. Doesn't need to access the DOM, doesn't need to access any APIs, but really something like compress this file or encode this video, for example. That's something that you can offload to a worker. You just have to write your code with consideration for this environment where you cannot access anything that you take for granted in your regular browser JavaScript. And again, this is probably the better solution if you don't need to touch the DOM. But in my case, I want to I talked about the browser extension where I just needed to read styles over and over and over again. That's really slow. So web workers were not really the proper solution for that. Again, this is a sort of problem that you really shouldn't have. But again, if you do, just add interleaving.
All right. So, and that's the end of the what is it called, the time slot. So, thank you very much for your time. Thank you for the presentation, and have a nice day.
Thank you. Until next time.
Until next time. Bye.